Welcome back to another video. We got lab 3, magnetic fields of a bar magnet. Let's get started. Well, what is this lab all about? Well, the main purpose is to measure the distance-dependent magnetic fields of a small bar magnet and then to compare the observed versus predicted distances of the on-axis and the off-axis magnetic fields that will be derived from the Biot-Savart law. And of course, for the predicted distances, as always, we're going to be using GlowScript as our computational model. And here's just a quick preview of the results. We have n to be this, and the magnetic dipole moment to be this. Time for the fundamental physics principles. And for the first time, we don't have Newton's second law. Although honestly, none of this would probably exist without it. So what do we have? First up is the Biot-Savart law, which was named after two French dudes who discovered the relationship between the magnetic field at a point to a tiny current element expressed by this equation. Next up, we got the magnetic fields of a dipole. Now, a magnetic dipole is just a closed circulation of an electric current system. Well, what does this mean? Basically, inside the magnet, we have a bunch of electrons circulating around atomic nuclei while spinning on its axis. This creates a dipole with magnetic field strength given by this equation. Finally, the distance dependence formula, which states that the magnitude of the magnetic field due to a bar magnet falls with distance and with this formula. We can also linearize this formula, as we will see in our graph soon. Let's get started with the experimentation. First, we need to orient our phone to make its magnetometer orthogonal to Earth's magnetic field. Side note, I know it's called magnetometer, but magnetometer sounds way cooler. You even got a whole superhero called that. Anyway, next we will need to find the location of the magnetometer chip on the phone by following these diagrams. Lastly, we will measure the distance between the magnetometer and the bar magnet for the on and off axis scenarios. And of course, for this lab, our system will be the bar magnet and the surroundings will be everything else. Okay, and here's the data for the on-axis scenario. To the left, we have the distance measurements for different magnetic field strengths. And on the right, we have the linearized plot of the averages. Now, based on our distance dependency formula and the equation of the line of best fit, we can determine the variables n and k. So now that we know n and k, we can solve for the magnetic dipole moment mu, which is found to be 4.613 ampere meters squared. Our next scenario is the off-axis magnetic field. This procedure is similar to what we did for on-axis, except now we have to move the magnetometer up and perpendicular to the direction of the axis. The results for the x, y, and z components of the magnetic fields at a perpendicular distance of 0.196 meters is given in the table. Now that we got the observed data out the way, we can move on to the computational model. The first step is to create a function for the magnetic fields and to set our initial conditions, particularly the magnetic dipole moment that we found in the previous steps. Here, I coded the visual aspect of the model. To do this, I specified the magnitude and direction of 2 on-axis arrows, 4 perpendicular off-axis arrows, and 1 arrow 45 degrees from the axis. The predicted magnetic field is highlighted in blue, which is relatively similar to our observed model, although there are some discrepancies. In this lab, we had to make a few assumptions and had room for potential error. The main assumption was that the bar magnet acted as a magnetic dipole, and the main error was that other electronic and magnetic objects in the room skewed with the magnetometer data. So here's just a quick little quiz about the observations made in this lab. The true statements are 1 and 4, which accurately describe the distance dependency formula in what we saw in this lab. For a deeper dive and discussion of the data, we have 2 what-if questions. I should for real become a rapper at this point. Anyway, first up, what if we hadn't compensated for the magnetic north and instead placed our meter stick at an intermediate angle relative to Earth's magnetic field? Well, the Earth's magnetic field would interfere with the bar magnet's magnetic field, and this would skew the results. Next up, what if we connected 2 identical magnets end to end and repeated all these experiments? Well, the magnetic field magnitude would roughly double, but the direction would stay the same. As per usual, thank you so much for your attention, and I hope you have a great day.